All right, let's go to 210.12, AFCI protection, arc fault circuit interrupter protection. Let's talk about the definition of AFCI. An arc fault circuit interrupter is a device intended to de-energize a circuit when it detects current waveform characteristics that are unique to an arcing fault. Now, the 2008 code is going to require the AFCI to be of the combination type. And see, the code is requiring AFCI. It's defining what AFCI, the characteristics of the waveform. Let's talk about what the characteristics could be. Now, you could have what is called a parallel arcing fault, and that would create a waveform that has a signature, that's the term they use, that looks something like this here. So this electronic device here has computers, processor in there, and it's looking for every single half waveform, and it's looking for the signature. Does it look like an arcing fault? And they've recorded what the signature are. If the answer is yes, the next thing it does is it checks. Is the peak of these arcing faults greater than 75 amperes? If the answer is yes, then what it does is it charges a capacitor. Here's where electrical theory comes in. It charges a capacitor. And I try to tell people, say, listen, imagine you had, let me just use this right here. You had two devices, and they're tied together with a bar between the two, and you have weight over here, and this weight is greater than, so it would go like this here, like a seesaw. If I could fill this sufficiently, I would be able to put enough weight that would cause this thing to rise. Well, the same thing happens. We have a capacitor here, that if I can put enough charge in this capacitor here, then I would be able to then raise it. How do you do that? Imagine we had holes, however, in this particular, where I'm going to be filling into. And so if we had holes, if I put water in here, the water is leaking out. So in order to get enough water in this container to force this thing up, I'm going to have water go in here faster than the water is going out. And that's how the capacitor works. The capacitor has a bleeding resistor, which means it's designed to discharge. But every time you have a signature of a waveform that looks like a parallel arc, and every time it's more than 75 amperes, it goes, bingo, charge the capacitor. If you can charge the capacitor fast enough with enough charges, you will get enough energy in the capacitor that will activate and operate the electronic circuitry that will say, open the breaker, turn off the circuit. Now, how many times does it have to charge? It works this way. If you can charge the capacitor 3 times in a row, half cycle, over 75 amperes, waveform, signature arc, yes, boom, charge. Second half cycle, yes again, boom, charge. Third half cycle, yes again, boom, charge. If you can take 3 half cycles over 75 amperes peak, you will charge the capacitor fast enough that will give the voltage that it needs to operate the circuit, turn off the circuit. You have a mic. You might not have it arcing every single second, or rather every single half. Here's where it works. It looks for the last 30 half cycles, and it counts how many times it was over 75 amperes and how many times it had a signature. So it has to have a combination of both. A motor might start, and it might be over 75 amperes, and it might be in a couple waveforms, but the problem is it doesn't have the signature. It doesn't count that. You might have an arc, but it's not over 75 amperes. It doesn't count that. So now, if you look at the last 30 half cycles, if it finds 9 of those, where did 9 come from? I don't know. It's just 9, whatever it is. 9 of those will give you, so it just keeps moving. Every 30 half cycles, it looks for 9 of those, and when it gets 9, it opens up the arc fault circuit interrupter, and then it turns off the power. That is when it's looking for a parallel arcing fault. What's a parallel arcing fault? Hot and a neutral. You take a hot and neutral and you compress the 2 wires together, and you have dielectric, which is going to be insulating material. But if you press those conductors tight enough, long enough, then you're going to get like this little arc. Here's the waveform. As it gets near the peak, it arcs and then extinguishes, and then it arcs and extinguishes, and it arcs. Take a look at this waveform that we're showing here on the slide. Now, there's a statement called RMS, which is the root mean square. This is over 75 amperes peak, but because of the signature, the way it works out, the RMS current of this might only be like 9 amperes. Well, if this is on a 20 ampere breaker, this on a regular inverse time breaker would be a load of, let's say, 9 amperes. But for an arc fault condition, it's still a 9 ampere load, but it has 1, 2, 3, it has a sufficient energy, and now operates the overcurrent device. So parallel arcing fault is this. You press the two wires together. It's arcing near the peak and it extinguishes and arcing near the peak. Well, there's not enough energy to operate a normal inverse time breaker because RMS-wise, in our example, was 9 amperes. But signature-wise and peak current-wise, arcing fault, the overcurrent device opens and clears the fault. Parallel arcing fault cause fires because hot and neutral conductors are arcing, but yet it's not sufficient to open the circuit protection device. Now let's go on to the second type where the combination AFCI protects against and watches. This one, and I'm not quite sure, and I got this from Cutler Hammer, why this is set at 6 amperes. But when you go to a series arcing fault, there's a couple of things that you have to do for series arcing fault. Number one, it has to have a signature of a series arcing fault, which is different than a signature of a parallel arcing fault. Looks similar, but it's slightly different. And Eric, you might understand this, and Kevin, you might understand this, which I don't fully understand. But let's talk about what a series arcing fault is. That's where you have a hot and a hot touching each other, and a hot and neutral touching each other, let's say at a terminal. But the terminal is loose. Hot is loose on the screw, or maybe the wire is cut and it's just kind of touching each other. And now in order for you to detect a series arcing fault, you have to have a load. The load that has to be connected on it is going to have to be 5 amperes. It's 5 amperes peak. It's not RMS. It has to be 5 amperes peak current, and it's just kind of arcing. It's called a glowing terminal. And what I was told by Cutler Hammer was that, Mike, we are looking for a signature, but that signature has high frequency. And I don't understand quite what's going on with arcing and where frequency becomes in. And I said, Mike, we don't work the same way that we're charging a capacitor every time we go up to the point. Rather, we don't count, let me phrase it, the arc charger, we don't count the number of waveforms in the last 3 out of 9. So series arcing fault, the electronics is slightly different than the parallel arcing fault, but you have to have a load because you can't check the series arc without the load. So now you have a parallel fault, which is hot neutral, series arc, which is the hot to the hot, loose connection, series arc, neutral to neutral, loose connection with a load. That's where the combination AFCI is and how it operates. This originated from the Consumer Product Safety Commission, having to do with cords that were plugged into receptacles that the table lamp was pressed on the cord, and it caused fires. And this was back in the early 1900s, early 1990s, and ultimately in the 1999 code, we got AFCI for the first time for receptacle outlets in dwelling units. The 2002 code expanded receptacle outlets to outlets in dwelling unit bedrooms, right? All the different receptacles as well as other outlets in bedrooms. 2005 code did not expand the requirements, and you're going to see in a second where we're at today on the 2008 NEC. All right, this graphic right here shows, from Cutler Hammer provided this, shows an arcing fault when you have no AFCI. See, here's AFCI on, that's off. It's no AFCI. It's a typical 20 ampere breaker. Then take the same picture but have it on an AFCI where the AFCI is operating. In this case here, you can see the difference between the intensity of an arcing fault with or without AFCI protection. This is what an AFCI device looks like. They're only made in circuit breakers, commercially available. And they're very similar to a GFCIs. You have that neutral to ground transformer that's in there that senses neutral to ground. It includes, as Kevin, you mentioned, some manufacturers not only have, here's what you have. You got an AFCI breaker. Ready for this? You have overload protection, right?
Yes.
You have short circuit protection. You have ground fault protection. That takes care of what? Overload. Okay, so now we have overcurrent. We have overcurrent. Okay, so now we have overcurrent protection. Then you have parallel hot to neutral sensing. That's your parallel arcing fault. It looks for the waveform signature and over 75 amps or so many, and then it opens for that condition.